Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
And welcome to a deep dive that I think is for anyone who's ever been just completely blindsided by a thermal system that refuses to cool down.
Oh, we've all been there. You follow the rules from the textbook, right?
Oh.
You add more fins, you switch to copper, you run the sim, and you think, I've nailed this.
And then you build it, you power it up.
And the temperature drops by, what, a few degrees? When you really needed 30, it is absolutely maddening.
It's so frustrating. And it's because thermal management is, it's a game of these invisible resistances. If you optimize the wrong one, you're just wasting time and money.
So that's our mission today. We're going to isolate 5 fundamental, recurring reasons why these thermal designs just stall out. We want to help you stop chasing those tiny gains.
And instead focus on the core physics that actually dictates the system temperature. We're going to look at everything from microchips to these massive industrial heat exchangers.
Okay, so our blueprint is to find the 5 invisible walls that heat just can't seem to get through. This is about helping you stop just throwing copper at a problem and start optimizing the right part of the system.
Let's start with, I think, the most intuitive one, but also the most misunderstood. The trap of just assuming more surface area is always better.
But isn't that the golden rule of convection? I mean, if I want to get more heat into the air, I need more area for the air to touch. Why doesn't doubling the fins give me double the performance?
Because you hit a point of diminishing returns, and it's governed by 2 main things. The efficiency of the fin itself, and then the fluid mechanics of the air flowing over it.
Okay, let's break that down. Start with fin efficiency.
Right, so we use the term fin efficiency. We call it ETA to measure this. If a fin is too long or, say, too thin, the heat just can't make it all the way to the end.
So the tip of the fin is much cooler than the base.
Exactly. And by the time you get to the tip, the temperature difference between the fin and the air is so small that it's barely transferring any heat at all.
So you've just got this expensive piece of metal sitting out there doing nothing. It's basically just mass.
It's wasted mass.
Yes.
That's a perfect way to put it. For a well-designed fin, you're looking for an efficiency, an ETA, of somewhere between, say, 0.5 and 0.7.
And if it's lower than 0.5?
The heat isn't getting out there. You need to make your fins shorter or maybe thicker. You're just not using the material effectively.
Okay, so I optimize my fin geometry. I hit that 0.5 to 0.7 range. I've solved the material side. But you said there's a second problem. The airflow becomes the bottleneck.
That's where the boundary layer takes over. I mean, even if you had infinite surface area, if the air can't physically get there to pick up the heat, you've got nothing. The heat is trapped.
Yeah, you see this with really tightly cacked circuit boards. The air just feels stagnant.
Precisely. If you look at vertical plates cooled by natural convection, which is super common in electronics, there's this fascinating thing that happens if the boards are too close.
The boundary layers from each board merge together.
They do. They merge and they literally choke the flow path. The air can't get through to carry the heat away, and your overall heat transfer just plummets.
So there has to be an optimal spacing.
There is, and it's all about optimizing for the fluid dynamics. There's an actual mathematical correlation for it. For symmetric isothermal plates, this optimal spacing, or BOPT, is 2.714 times P to the power of 1/4.
That's incredibly specific. But the point is, it's not just some academic number. Getting that spacing right can be the difference between a working design and a failure.
It really can. It's a fundamental redesign, not just a marginal gain.
Okay, that leads perfectly into the second failure point, the hidden barrier,
Yeah.
contact resistance. Because you can have the best heat sink in the world,
Yeah.
but if the heat can't get into it,
Then all that work is for nothing. And contact resistance is, I think, the most insidious one because it's microscopic. We think of 2 flat metal surfaces, and we assume they're perfectly touching.
but they're not. They're only touching at these tiny little peaks, these asperities.
Right. Only a tiny fraction of the area is actually making solid-to-solid contact. The rest is just a gap, usually filled with air, which is a great insulator.
So the heat has to squeeze through those tiny contact points.
Exactly. That joint resistance, R sub J, is super complex. If you ignore radiation for a second, it's basically 2 paths in parallel. You have the heat going through the microcontacts, and then you have heat trying to get through the gas in the microgaps.
And this is where we use thermal interface materials, right? The thermal grease or the pads. But it sounds like even they are fighting a losing battle against the surfaces themselves.
They are. The resistance of the TIM itself, R sub TIM, depends on its thickness and conductivity, sure. But it also critically includes the contact resistance, R sub CO, which is dominated by the surface roughness of your 2 parts. Let's call them Sigma 1 and Sigma 2.
Hold on. So if I buy the world's most expensive thermal grease, but I put it between two really rough, poorly machined surfaces.
The roughness kills the performance,
Yeah.
absolutely. Because those rough surfaces create bigger gaps, which means you need a thicker layer of grease to fill them. And that just increases the resistance.
So spending time on a better surface finish might be way more valuable than spending money on a slightly better TIM.
Often, yes. Think about industrial stuff like air coolers with high-fin tubes. If you just press fit the tubes into the plates, you have to assume there's going to be a huge, unpredictable contact resistance.
But if you braze them,
If you braze them, you create a metallurgical bond. It's fused. The contact resistance basically goes to zero. It's all about the interface mechanics, not just the material.
which brings us to failure number 3, and this one is a classic. Why did switching my material from aluminum to copper barely change the temperature?
Ah, yes. The great material switcheroo. This is all about system resistance dominance. You've just successfully optimized the wrong link in the chain.
You have to think of it like a circuit, a series of resistors.
Exactly. Heat has to flow from the source through the solid into the coolant. In a big heat exchanger, you might have like 5 resistances in that chain.
5, what are they?
You've got the hot side convection, then hot side fouling, then the conduction through the wall itself, then cold side fouling, and finally cold side convection.
And the material choice, the copper or aluminum, that only affects one of those 5, the solid wall conduction.
And if that one link is only, say, 5% of the total resistance in the system, you could use a material with infinite conductivity and you'd still only see a 5% improvement.
The problem is somewhere else. It's being dominated by convection or what's fouling.
Fouling is huge in industrial settings. It's just junk. Scale, rust, sludge, whatever, building up on the surfaces and forming an insulating layer.
Like putting a tiny little velvet jacket on your heat exchanger.
A very effective insulating velvet jacket. The Tubular Exchanger Manufacturers Association, TEMA, even publishes fouling factors. For something like heavy fuel oil, that fouling layer can easily be the single biggest resistance in the whole system. Your choice of metal becomes totally irrelevant.
Wow. And you mentioned something about complex electronics too, anisotropic conductivity.
Right. In a printed circuit board, it's a composite of copper and FR4. The heat might flow really well sideways through the copper planes.
But terribly downwards through the fiberglass substrate.
It's like a racetrack in one direction and molasses in the other. You can't just use one bulk conductivity number for the whole board in your analysis. You have to model the layers or you'll get it completely wrong.
Okay, so that covers the steady state world. Our 4th failure point is about timing. How do I estimate heat up or cool down time? Why does my steady state thinking fail me here?
Because predicting the final temperature is a totally different problem from predicting how long it takes to get there. That's transient analysis. It's critical for anything with pulsed power microprocessors, lasers, things that turn on and off really fast.
And the tool everyone reaches for first is the lumped capacity solution. Where do we go wrong with that?
Well, lumped capacity is beautifully simple. It just says the rate of temperature change, dT over dt, is the heating rate Q divided by the mass times the specific heat, C sub P.
It assumes the entire object is at one uniform temperature at all times.
And that's the trap. That assumption is only valid if the object has really high thermal conductivity, so heat can spread through it almost instantly.
So if you use it on something with low conductivity, like a big chunk of plastic,
The surface temperature will skyrocket while the inside is still cool. The model's core assumption is violated, and you will dramatically underestimate the peak temperature during that heat-up phase.
and for something complex like a chip package, it's not even one smooth curve, is it?
Not at all. There are actually 4 distinct phases. First, the chip period, where the heat is just inside the tiny silicon die. Then an intermediate period where the die bond and encapsulant get involved. Then a quasi-steady period where the whole package starts to heat up. And finally, you reach steady state.
So for pulse power, you have to model those early stages correctly.
You do. You can't use a simple model and expect an accurate answer for those very fast transients.
Which leaves our 5th and final failure point, radiation. I think we all tend to ignore this unless something is literally glowing red hot. So when does it matter at lower temperatures?
You're right. The classic thinking is that radiation depends on the 4th power of absolute temperature. You know, the heat transfer rate, Q sub R, is proportional to T1 to the 4th minus T2 to the 4th, so it dominates at high temps.
Right. If my controller's at 50 Celsius in a 20-degree room, I'm thinking convection is doing all the work.
And that is the big surprise. Here's the aha moment. For small temperature differences, like on the order of 10 Kelvin, the effective radiation heat transfer coefficient.
There's a coefficient for it.
Yeah, we call it H sub r. For an ideal black surface, that coefficient is approximately equal to the heat transfer coefficient for natural convection in air.
Wait a minute. You're saying that at near room temperatures, radiation can be responsible for half of the total heat transfer. It's a 50-50 partner with natural convection.
In many common passive cooling scenarios, yes, that completely changes the calculation. And it means you suddenly have to care a lot about surface properties, specifically emissivity or epsilon.
Which is just a measure of how well a surface radiates heat compared to a perfect black body.
Exactly. So if you take your shiny aluminum heatsink and you paint it matte black with a high emissivity coating, you can potentially double its performance without changing the airflow at all.
But the flip side is, what happens over time?
That's the other trap. Surface aging. In the real world, surfaces oxidize, they get dirty. That pristine polished aluminum from your CAD model might, after 6 months, have a completely different emissivity. It acts like a different material, thermally speaking. You have to design for the real aged surface.
This has been a total teardown of the common failure modes. So to recap, adding surface area fails because of fluid mechanics. Switching materials fails because another resistance, like convection or contact, is the real bottleneck.
Transient estimates fail because we misuse simple models, and radiation is a silent 50-50 partner to natural convection, even when things aren't hot.
The big lesson here is that it's all about managing a chain of resistances.
It is. Stop asking, how do I make this heat sink better?
And start asking, which of these 5 resistances is the single biggest bottleneck in my system right now?
That's the question. And that leads to one final, maybe provocative thought. We've been talking about managing these resistances, which is really about managing thermodynamic inefficiency. But what if we use that inefficiency as our actual design guide?
So look beyond just making the temperature lower.
Exactly. I'd challenge you to look into something called entropy generation minimization, or EGM.
Okay, that sounds pretty advanced.
It is, but the goal is elegant. It guides you to the optimal physical design, the dimensions, the shapes, the materials, by directly linking thermodynamic non-ideality, like temperature differences and pressure laws, to the physical system itself.
So it's not just how hot is it, but also how much energy am I wasting to pump this fluid. It's a total system view.
It forces a holistic view. You're not just minimizing temperature, you're minimizing the total entropy generated by all the irreversible processes in your system. By doing that, it guides you to the true balanced optimum, not just the one that's least bad in one category.
That's a really powerful framework. Thank you for guiding us through all these invisible forces that can really sabotage a design.
My pleasure. Until next time, keep digging deep.